All right, everyone. Today, we're going to get to the very heart of wave optics. We're moving beyond just looking at the cool patterns and diving into the actual mathematics that lets us predict and even engineer these phenomena. We're talking about interference, and to really get it, you have to understand the math. So let's jump right in.
You've all seen this, right? The beautiful swirling colors on a soap bubble? You might think it's just some kind of magic, but it is pure, unadulterated physics. And by the end of this, you won't just understand why it happens, you'll be able to calculate the exact conditions that create those colors. The answer is all in the math of waves.
Okay, so first principles. Interference, at its core, is just what happens when two or more waves show up at the same place at the same time. The principle of superposition tells us they just add together. Simple enough. But how they add together, well, that is where things get really interesting. Let's start with the best-case scenario. Imagine two waves arriving at a single point perfectly in sync. A peak from one wave meets the peak from the other, trough meets trough. They just reinforce each other, right? Their amplitudes add up, creating a brand new wave with a much bigger amplitude. For light, a bigger amplitude means more intensity. In other words, brighter light. We call this constructive interference. Now, on the flip side, what if they arrive perfectly out of sync? A peak from one wave meets a trough from the other. Well, now they're working against each other. And if their amplitudes are the same, they will completely cancel each other out. You get zero amplitude. For light, that means no intensity. You get darkness. That's destructive interference. And really, these two outcomes, bright and dark, are the fundamental building blocks of every interference pattern you'll ever see. So, this leads to the crucial question: what causes two waves that might have even started from the same source to arrive at some destination either perfectly in sync or totally out of sync? The answer, believe it or not, is just simple geometry. It all comes down to the path they travel. Let's look at the textbook example, Young's double-slit experiment. We have light passing through two tiny slits, and those slits then act like two new, perfectly synchronized sources. Now, just pick a random point on that screen over there. The path from slit A to that point, which we'll call RA, is obviously not the same length as the path from slit B, RB. This simple difference in distance is what we call the path difference. And this idea isn't just for some lab experiment with slits. It applies right here to a thin film of, say, oil on water. Ray 1 bounces off the top surface. Ray 2 actually travels into the film, bounces off the bottom, and then comes back out. You can clearly see that Ray 2 traveled a longer path. So, once again, we have a path difference. So let's put a formal name on this. We call it the optical path length difference, and we denote it with a delta L. And I want you to burn this into your brain. This single, simple, geometric value, just the difference in how far two waves travel, is the root physical cause of every single interference pattern you will ever see. It is the bridge between the physical setup and the final outcome. Okay, now that we have the physical cause, the delta L, let's build the mathematical engine that connects it to the result. We need a way to translate that physical distance, that path difference, into what really matters for waves, their phase difference. And the process for doing this is wonderfully logical. You can break it down into three clear steps. First, you identify the two separate paths the waves are taking, just like we did. Second, you calculate the geometric difference in their lengths, that's your delta L. And then the third and final step is to convert that length difference into an angle, the phase difference, which we denote with delta phi. And this is the engine that does the conversion. This is the crucial equation. The phase difference, delta phi, equals the path difference, delta L, multiplied by this factor of 2 pi over lambda. You can just think of 2 pi over lambda as a conversion factor. It makes sense, right? For every full wavelength of distance a wave travels, its phase changes by 1 full circle, or 2 pi radians. This equation just scales that idea, turning any path difference into its equivalent phase difference in radians. This quote just sums it up perfectly. The path difference comes from the geometry of your system. The spacing of the slits, the thickness of a film. You calculate that first. Then you plug it into our equation to find the phase difference. And it's that phase difference that tells you definitively if you're going to get a bright spot or a dark spot. So now we have all the tools we need. We can finally move from just setting up an experiment to precisely predicting the pattern it's going to produce. So let's define the exact conditions for those bright and dark fringes we talked about.
So when you see a bright fringe, a maximum, that's happening where the waves are arriving in phase. They are adding constructively. What does that mean for our math? It means their phase difference, delta phi, has to be 0, or 2 pi, or 4 pi, basically any integer multiple of 2 pi. They might have traveled a different number of full cycles, but they meet up at the exact same point in their cycle. This table right here, this is your cheat sheet. For constructive interference, a bright fringe, the path difference, delta L, has to be a whole number of wavelengths, 0, 1, 2 wavelengths, and so on. For destructive interference, a dark fringe, the path difference has to be off by a half wavelength, so 1/2, 1.5, 2.5, you get the idea. Understanding these two conditions is everything. All right, let's put these rules to the test. Let's go back to our thin film problem. But I want you to be careful here. The real world often has an extra little twist. And for an engineer, paying attention to the details is everything. So here's our setup one more time. An incoming ray splits. Ray 1 reflects off the top surface, where light is trying to go from a less dense medium, like air, to a more dense medium, the film. Ray 2 reflects off the bottom surface, where it's going from a more dense medium, the film, to a less dense one. This distinction is about to become incredibly important. And here is the twist. This is a critical detail. There is a rule in optics that says whenever a wave reflects off a boundary with a medium that is optically denser, it undergoes an instantaneous phase shift of pi radians, or 180 degrees. So in our diagram, ray 1 gets an extra pi phase shift just for bouncing off that top surface. Ray 2, however, does not, because it's bouncing off a less dense boundary. And look at what this does to our rules. That single pi phase shift flips our conditions completely upside down. For the waves to interfere constructively now, the path difference actually needs to be off by half a wavelength to cancel out that reflection shift. So the condition for a bright fringe becomes the old condition for a dark one, and the condition for a dark fringe becomes the old one for a bright one. The rules have inverted. You have to account for this. And this brings us all the way back to our soap bubble. The bubble is just a thin film of soapy water, right? Its thickness is constantly changing as the water swirls around. At any given point, that thickness creates a path difference that will cause constructive interference for one specific wavelength, one specific color of light. And as the thickness changes, the color that gets reinforced changes right along with it, creating that beautiful, shimmering pattern. It's not magic, it's just math and physics. So there you have it. We've connected a physical thing you can see with your own eyes to a clear, predictable mathematical framework. You now have the tools to analyze this stuff. So I'll leave you with a question to chew on. Think about where this really matters. How would you use these exact principles to design an anti-reflective coating for a camera lens? Or how is this used to build incredibly precise measurement tools like interferometers? The physics you've learned today is the foundation for a huge range of modern technology.